Hello students, welcome to this lecture number 11 on chemical bonding and molecular structure. Valence bond theory do not able to explain some of the properties of the molecules and its ions, like the magnetic property, that is the diamagnetic property or paramagnetic property, and also it could not able to explain the relative bond length and bond strength of the molecules. And to explain all this behavior of the molecules that has not been able to explain by the valence bond theory, one new theory is put forward, that is MO theory. MO theory is put forward to explain all those unexplained things which as per the valence bond theory. And this MO theory, we can say this is molecular orbital theory. Molecular orbital theory. In the short form, it is also called MOT. This theory has been developed by two scientists, that is R.A. Mulliken and another is Hunt, H-U-N-D, Hunt. The two scientists has developed this very important theory, and in this lecture we are going to discuss the main points and the related things as per your syllabus that we will be going to discuss in this lecture. So today's lecture regarding the MO theory, molecular orbital theory. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. First, let us understand what are the silent features, main points of this theory. This theory is very much unique. It says when two atomic orbitals has been combined, it will lost its identity and form a new orbitals, that is called the molecular orbitals. As electrons in the atoms is present in the atomic orbitals, in the molecules the electrons are present in the molecular orbitals, and that is the new concept put forward by the scientist. So this is the first point in this theory, that is ABMO. This is the first postulate, that when two AO, that is atomic orbitals, combines, it is going to form a new orbitals. The atomic orbital will lose its identity, and this new orbitals is called the molecular orbitals. And there are two types of molecular orbitals produced from the combination of the AOs, that is the bonding molecular orbitals, and another is anti-bonding molecular orbitals. Second point basically is how these atomic orbitals have been combined to form the molecular orbital, and by principle of LCAO, this is called linear combination combination of atomic orbitals. The bonding molecular orbital, that is BMO, is formed by the addition So this is the second postulate. By principle of linear combination of atomic orbitals, the bonding molecular orbital is produced by the addition of the wave function of the atomic orbitals, and the anti-bonding molecular orbital is produced by the subtraction of the wave function of the electron wave of the atomic orbitals. So suppose there is the two atoms, atom A and atom B, having the wave function is phi A of atom A, and atom B is wave function is phi B. So at that time, bonding molecular orbital BMO, that is designated as sigma, it will be mathematically can be expressed phi A plus phi B, and ABMO, that is sigma star, it is also phi A minus phi B. So this is how a atomic orbitals has been combined to form a molecular orbitals. Two atomic orbitals will combine to produce two molecular orbitals. Now we go to the third number points of this theory, that the energy, we can write energy of BMO and ABMO can be understood that is, suppose this is a 1 AO atomic orbitals and this is another atomic orbitals. We can easily understand one thing. This energy of the bonding molecular orbitals is less than the atomic orbitals. So we can write BMO energy is less than the atomic orbitals from which it has been formed, and ABMO have the energy greater than the atomic orbitals from which it is being formed. Now how the BMO has the lower energy and the ABMO has the higher energy? This is because in BMO the electron density in between the nucleus. So the electron will attract the nucleus and the molecule will be bonded to each other by the electrons, and this will stabilize the molecules very well, and it will have the lower energy to the system. At the same time, the ABMO, so you can write this here, you can make a diagram of this. This is a BMO. BMO here, this is the nucleus and this is a nucleus, and electron density in the nucleus. Whereas in ABMO, you can see the nucleus distance, the electron density is away from the nucleus. This is the two nucleus, and here there is a nodal plane. There is no electron density between them, and there is a repulsive force in the antibonding molecular orbital. When you put the electron there, there will be repulsion, which basically that repulsion between the nucleus and between the electron also, and that will destabilize the molecule, and it will going to create the higher energy in the bonding antibonding molecular orbitals. So we understand the energy of BMO and energy of the ABMO, that is BMO is lower energy and ABMO is higher energy. Now that is the fourth point, the conditions for the conditions of LCAO, that there are basically 2-3 conditions, and satisfying of which the combination of the atomic orbital will be possible. The condition, number one condition, the energy. Energy of the combining atomic orbitals will be same. Energy of AO atomic orbitals should be same. That is, we can say the 1s orbital will combine with 1s orbital combined with another 1s orbital, not with the 2s orbital. Okay. Second thing, in case the orientation is not perfect, the actual orientation of the combining molecular atomic orbitals will be same. So second point, that is orientation. Orientation of AO. If the orientation is same, at that time only there will be the combination with the AOs, atomic orbitals. If the Z axis is the internucleus axis, then S orbital will combine with the P2PZ orbitals. PZ orbital, you can say 2s orbital combined with the 2pz orbital, not with the px orbital, 2px orbital or 2py orbital, because their orientation is not same. And 2pz orbital will combine with another 2pz orbital, not with 2px, 2py, because of the orientation. So these are the conditions for the linear combination of the atomic orbitals. Now we are going to use types of molecular orbital. The types of molecular orbital, that is being designated at sigma, pi and delta, and this is for bonding BMO bonding molecular orbital, and for anti-bonding molecular orbital sigma star, pi star and delta star, it is ABM. Now what is the difference between the sigma and pi molecular orbital? Let us understand. Sigma orbital is symmetric around the bond axis, whereas the pi orbital is not symmetric around the bond axis. So here you can see 1s orbitals, 1s orbital plus 1s orbital, it will going to produce the sigma 1s orbitals, that is bonding, and another sigma star orbital. 2s orbital and plus 2s orbital will produce the molecular orbital sigma 2s orbital and sigma orbitals. Then 2px orbital, 2pz plus 2pz orbital, it is going to create sigma 2pz orbital and sigma star 2pz orbital. Okay, and 2px plus 2px orbital, it will going to produce the pi. In this case, pi anti-bonding molecular orbital, you will find 2px and pi dash 2px is produced. And this is will be same for the 2py also. In the 2py also you will find that it will produce 2py and antibonding 2py. So these are the molecular orbital produced from these respective atomic orbitals. Now we are going to discuss the shape of this molecular orbital. Shape. What will be the shape of this MO? Or pi to py. So you can see this is the shape of the molecular orbitals. This is for sigma 1s bonding. This is the bonding molecular orbital. Sigma 1s, sigma 2s, sigma 2s, 1s or 2s. This is anti-bonding sigma 1s or sigma 2s. This is sigma 2pz. 2pz orbitals, and it is anti-bonding 2pz orbitals, and it is 2px and 2pa bonding orbitals, and this is anti-bonding orbitals. So this is the shape of the orbitals. Now we are going to discuss the electronic configuration. Electronic configuration of molecular orbitals. Electronic configuration of molecular orbital will be made as per the above principle what we follow for the atomic orbital also. Means the published exclusion principle and also the Ohm's rule of maximum multiplicity. So for that, as per above principle, you have to arrange the electron in order of increasing the energy of the molecular orbitals. So what is the molecular energy of the molecular orbital? Let us understand. In this case, there is basically two label diagrams of the molecular orbitals, that is one that is up to N2, because here it is observed 2s and 2p orbital mixing. 2s and 2p orbital mixing is there, right? And 2s and 2p orbital mixing is there, and at that time you will find the order of filling of this molecular orbital will be this way. Sigma 1s will be first filled, then anti-bonding sigma 1s, then sigma 2s, then we have to feel the pi to px is equal to pi to py. Then we have to fill the sigma 2pz orbital, and after that there will be the anti-bonding. And then sigma anti-bonding to pz. In this way, as per the energy of the molecular orbital has been increasing in this fashion up to O2. But for up to N2, for O2, F2 and Ne2, and there is a slight differences in this. Let us understand. That is sigma 1s, sigma star 1s, then sigma 2s, sigma star 2s, then this will be changed, then sigma 2pz followed by pi 2px is equal to pi 2pz, then pi star antibonding to px is equal to pi star antibonding to py, and then sigma 2pz. This is the order of filling the electrons in the atomic molecular orbitals. Okay, so this is a very important thing to understand. It is very simple. Now 8 point information, we get information from molecular orbital configuration. What information we get? Number 1 we get, that is the bond order. Very, very important thing. Bond order. Bond order is the BO is equal to half NB by NA. NB is number of electrons in the bonding molecular orbitals. Na is the number of electrons in the anti-bonding molecular orbitals. And from this bonding order, we can able to know about the formation of the molecule. Formation of molecules. If the bonding order is 0, then we say the molecules will not going to be formed. Second thing, the stability. Stability of the molecules, that we are able to know from the bonding orders. Third thing, that is the bond dissociation energy. Bond dissociation energy. Dissociation energy. And fourth thing, that is the bond length. So all this thing information we can get from this bond order. Another information that we can get from this configuration, molecular orbital configuration, that is the magnetic property. Basically, magnetic property. Magnetic property is basically two property. One, that is the dimagnetic, means substance will repelled by the magnetic field. Repelled by magnetic field. This is called magnetic field. And second thing, that is paramagnetic. Paramagnetic is the attraction by magnetic field. So attraction by the magnetic field is a paramagnetic, and it is repelled by the magnetic field, it is a diamagnetic. In the electronic configuration, when all the MO molecular orbitals occupy by double electron, means electron occupied by paired electron, you can say paired electron, then we can say the substance or molecule will be diamagnetic. Electrons will occur or it will be occupied doubly, but here in the paramagnetic it will be unpaired or singly occupied. Unpaired or singly occupied. Then we will call it is a paramagnetic. So this we can easily understand when we take some example of the molecules. Molecule we have first taken, that is H2, hydrogen. Hydrogen, you know, it is 2 electrons, and so its configuration, molecular orbital configuration will be this. Both the electrons will occupy by the bonding 1s sigma orbitals, molecular orbitals. So bonding order will be, that is 2 minus 0 by 2, that will be 1, and it is doubly occupied. The electrons are paired here, so it will have the diamagnetic. Then we are taking the example helium molecule. Helium molecule, that we know it will have the 4 electrons, and these 4 electrons will be arranged in the molecular orbital in this fashion. 2 electrons in the bonding molecular orbitals and another 2 electrons in the anti-bonding molecular orbitals. So here bonding order will be 2 minus 2 by 2, that will be 0. Means this molecule is not possible. Molecule is not possible because bonding order is 0. Then we are taking another example, that is lithium 2. Now see whether lithium 2 exists or not. Lithium 2, that lithium has 3 electrons, so atom is 3 electrons, so molecule will be 6. So electronic configuration will be this. So bonding order will be 2 electrons in the total 4 electrons. 4 electrons in the bonding MO, bonding molecular orbitals. So this will be 4, and 2 electrons in the anti-bonding molecular orbital, that is 2, and it will be 2, and it is bonding order is 1, and this molecule is possible. In the vapor phase we observe this presence of this molecule. Now we are going to take the electronic configuration of the carbon molecule, carbon C2. Then this molecule configuration will be like this. It will be total 12 electrons, not 6. 6, that is for one atom. So we have already placed 2 to 8 electrons, and here in the next we will be placed to P. So this will be the electronic configuration of this C2 carbon molecule, and its bond order, if we calculate, you will find it will be coming around 2. So it is diamagnetic because here lithium also it is also diamagnetic. So you understand how do we able to make the electronic configuration of the molecules, molecular orbitals in case of different molecules. Now we are taking the example of oxygen. Oxygen we know having 16 electrons. So here this molecular orbital configuration will be 6s2 here there will be changes because first sigma 2 pz will be filled. So we will write this sigma 2 pz whole square. Then we have sigma 2 px square is equal to sigma 2 ps square, means there are 2 electrons. It is not square, it is 2 electrons. The total electrons we have filled 1, 2, 3, 4, 5, 6, 7, 14 we have filled, and another 2 electrons will be in the anti-bonding pi orbital 2px is equal to pi 2px, and it will have the singly occupied. So this is the bonding order will be, we will calculate, it will be coming around 2 volts. So it is, you can see that is different from the others configurations, other electronic configuration. Here you can see it is the 2 px and py orbitals has been singly occupied. That is, it is a paramagnetic. Okay. So in this way we can able to write the electronic configuration of the molecular orbitals. Okay, I think that is clear to you. Hydrogen and lithium too have same stability, have same bond order, not stability, same bond order. But what about their stability? Stability will be same or different. For that, let us understand, let us see the bond, calculate the bond order of H2. We already know this is bond order is 1, we have already calculated, and Li2 we have already calculated. Lithium sigma 1s2 square sigma star square sigma 2s is 6 electron. So this bond order will be 1. In spite of this fact, this bond order is same, but stability of the hydrogen molecule is much more as compared to the lithium, because here in the anti-bonding orbitals, molecular orbitals, there is a presence of the electrons. So this type of things in exam may understand what bond order is same, but what about its stability? So stability of hydrogen will be greater than the stability of the lithium. Okay. So that is all for today's lecture. In this lecture we have discussed totally the molecular orbital theories and these main points, and how we can able to predict the configurations, how we can able to predict the magnetic property, how we can able to predict the bond order, how we can able to predict the stability of the molecules, that we all understand. And if you like this video, you can share to your friends. Thank you very much for listening.